Hello. We continue our course, and today's topic is the relational data model. In the first lecture, we dealt with the conceptual level of design. We got acquainted with the general principles of domain analysis and learned to analyze and capture it in the form of diagrams. This lecture is a direct and logical continuation. It serves as a bridge between the visual diagram understood by the analyst and the strict, formalized structure understood and controlled by the computer system. Here is the plan for our work today. We will move strictly according to these points. First, we will lay the theoretical foundation. Define the formal terminology of the relational model so that we speak the same language. Next, in the second section, we will look at the practical core of the lecture. A clear algorithm that shows how to turn an diagram, which we met last time, into a set of correct tables. In the third section, we will discuss the guarantees provided by this model. That is, what mechanisms exist to protect data from corruption or loss of logical links. After that, we will look at how this model manipulates data and what the revolution of the declarative approach was. And we will finish the lecture with an objective analysis of the advantages and disadvantages of this model, which will logically lead us to the topic of the next lecture. So let's start with the first point, formal terminology. So let's start where we left off last time. The first lecture was dedicated to the conceptual level. We captured the business requirements of our university in the form of diagrams, defining entities such as student or department, and the relationships between them. This was the semantic stage. We answered the question, what to store? Today we are moving to the logical level. Our task is to turn these flexible diagrams into a strict, formalized structure that a computer system, i.e. a DBMS, can understand and control. And to understand the revolutionary nature of the relational model, we must first understand the problem it solved. Before it, hierarchical and network models dominated. Their fundamental flaw was the lack of data independence. This means that the program logic was rigidly tied to how the data physically lay on the disk. As shown in this illustration, the programmer had to manually pave the route along these links, as if following pointers. To find a student of a certain department, one had to write a procedure. Take the pointer to the department, go through all its pointers to lecturers, take the pointer to the lecturer, go through his pointers to groups. It was complex and incredibly fragile. Any change in physical data storage required rewriting programs. It was this problem, the lack of independence, that Edgar Cod set out to solve. And his solution was brilliant in its foundation, as we will see on the next slide. So, on the previous slide, we identified the problem, rigid coupling to physical pointers. The solution proposed by Edgar Cod was brilliant. He shifted the foundation of databases from engineering to pure mathematics. He decided that the data structure should be based not on how a hard disk works, but on abstract provable theory. And he found it in set theory. Why exactly this? Because it provided two key principles that automatically resolved the chaos of older models. First, the principle of uniqueness. As you know from mathematics, there cannot be two identical elements in a set. This is a fundamental requirement. This means that in our students table, there cannot be two absolutely identical rows. The model simply won't allow them to be created. This principle is the theoretical basis for the primary key, which we will use for unique identification. Second, and this is the main breakthrough, elements in a set have no order. Set ABC is the same as set CAB. This automatically gave us data independence. It no longer matters to us in what order students were physically recorded on the disk. Logically, the set remains the same. The DBMS itself decides how to efficiently store and retrieve this data. Since the entire relational model is built on this strict mathematical apparatus, we can no longer rely on intuitive concepts like table or row. We are forced to use the formal terminology of this theory. This is not an academic whim, but a necessary condition for describing the rules and guarantees of the model accurately. Therefore, we move on to our formal vocabulary. So, as we established, the mathematical foundation requires a precise vocabulary from us. Let's define the three main concepts of the relational model. Its key structural components. First, relation. This is the formal academic name for what we all intuitively call a table. In Cod's theory, a relation is a set consisting of elements of the same structure. Second, attribute. This is the formal name for a column. This term is already familiar to us from the conceptual level. It describes one property of the entity we store, for example, a student's surname or a group name. Third, tuple. This is the formal name for a row or record. If a student is an entity, then one specific student, for example you, is an instance and the row describing you is a tuple. And here we immediately return to the principles from the previous slide. Since a relation table is formally a set of tuples, rows, this reinforces the requirement for uniqueness. There cannot be two absolutely identical rows in a table. On the last slide, we defined three main structural components. Now let's look at the rest of the terms needed to understand the model. The most important of the abstract concepts is domain. A domain is essentially a set of rules for a specific column. These are all the values it is allowed to accept. The best example from our university is the grade attribute. Its domain is integers in the range from 0 to 100. This means that the system will physically not allow writing the value 105, or the text string excellent, there. Or for example, the domain of the gender column can be a clear set of values. Male, female, not specified. Adherence to domains is the first and fundamental level of ensuring data integrity, which we will return to later. The other two terms, degree and cardinality, are simply table dimensions. Degree is the width of the table, that is, the number of its attributes or columns. When we design the students table and decide that it will have 5 columns, we define its degree. This is a static characteristic. Cardinality is the height of the table, that is, the number of its tuples or rows. Unlike degree, cardinality is dynamic. When a new student is enrolled in the university, the cardinality of the students table increases by 1. Thus, we have finished forming our formal vocabulary. We know all the components and their properties. Now we are ready for the main part of the lecture, the algorithm that explains how to build a working schema from these components that reflects our ER diagram. We have finished with the terminology. Now we begin the most important and practical part of today's lecture, transformation rules. As we remember, the conceptual model, our ER diagram, is a semantic blueprint. It captures the university's business logic, understood by the analyst. But a relational DBMS does not understand diagrams. It understands relations, i.e. tables. Therefore, the logical model is the engineering implementation of our blueprint. The transition between these two levels cannot be chaotic. We cannot rely on intuition. We need a clear, systematic algorithm. This algorithm, that is, the set of rules we will now consider, must provide a guaranteed answer to very specific questions. How exactly does an entity turn into a table? What to do with different types of attributes? And most importantly, how do we implement conceptual relationships, one-to-many and many-to-many, if there are no more arrows in our arsenal, but only primary and foreign keys? This set of rules is the core of logical design. Let's look at the first of them. So, we begin examining the algorithm. The first set of rules concerns the entity itself, that is, what to do with the rectangle and its ovals from our diagram. The rules are very logical. Rule 1 states that each strong entity, such as student or group, transforms into a separate table, which we now formally call a relation. Simple attributes of this entity, like date of birth or group name, simply become columns in this new table. Rule 2 concerns composite attributes, which we discussed in Lecture 1. If we had a full name attribute, we do not create a single full name column. To ensure the correct operation of the model and the ability to search or sort, we must atomize the data. Therefore, full name turns into 3 separate columns: last name, first name, and middle name. And Rule 3, the most important in this block, concerns the identifier. The unique identifier we defined at the conceptual level, most often a surrogate key like student ID, becomes the primary key or PK of our relation at the logical level. It is this mechanism PK that will guarantee the uniqueness of every row, as required by set theory, which we talked about earlier. So, we figured out how to create separate, isolated tables. Now for the most difficult part of the algorithm, how to implement connections between them. So, we have defined how to create isolated tables for entities. Now we must link them. Rule number 4, which we are now considering, is fundamental to all relational design. It describes the implementation of the most common relationship, one-to-many. A classic example in our university: one group has many students. The relational model has no arrows or pointers. It implements this relationship using data, specifically through the foreign key mechanism. The algorithm is always the same, and it is very important to remember the direction. The key always migrates from the one side to the many side. That is, we take the primary key of the groups table, which is group ID, and add a new column with the same or similar name to the students table, where it becomes a foreign key. As you can see in this diagram, now each table has its own PK, but the students table has an additional group ID column marked FK. If student Ivanenko has the value 5 in this column, it means he is logically linked to row 5 in the groups table. Thus, the connection is established. This was a relatively simple situation. But what if the relationship is more complex? Many-to-many? We sorted out the one-to-many relationship. Now let's move on to a more complex but very common situation: many-to-many. A classic example at a university. One student studies many courses, and one course, in turn, is attended by many students. First and foremost, remember, the relational model cannot implement an M relationship directly. We cannot use the rule from the previous slide. You can't add an FK to the students table because a student has many courses, and you can't add an FK to courses because a course has many students. Neither option will work. Therefore, any M relationship is always resolved by creating a third intermediate table. This table is called an associative, or junction table. As you can see in this diagram, we created a new table which I named enrollments. Its sole purpose is to link one student row with one course row. Structurally, it necessarily contains at least two foreign keys: student ID, which refers to the student's PK, and course ID, which refers to the course's PK. Each row in this table is a fact. Student X is enrolled in course Y. Note, this new table is the perfect place to store attributes that describe the relationship itself. For example, grade for the course. The grade does not belong to the student because he has many for different courses, and does not belong to the course because there are many different grades on it. The grade belongs precisely to the fact of a specific student's enrollment in a specific course. Thus, as the diagram shows, we neatly broke one problematic M relationship into two correct 1M relationships. And finally, the last sixth transformation rule, which concerns weak entities. Let's recall from the first lecture. A weak entity is an entity that ontologically, that is, by its very nature, cannot exist without its owner entity. A classic example is a student's phone number. By itself, a phone number makes no sense in the university database. It exists only as an attribute of a specific student. Although, since a student can have many phones, we move this into a separate entity. The transformation rule here is as follows. A weak entity also turns into its own separate table. But its key difference is the structure of its primary key. Its primary key is always composite. As you can see in this diagram, the primary key of the student_phones table consists of two parts. First, it is a foreign key, student ID, referring to the owner students table. Second, it is its own partial identifier, in our case the phone_number itself. Thus, row uniqueness is guaranteed by the combination student ID plus phone_number. This is logically correct since a phone number is unique only within a specific student. This structure also guarantees that a phone record cannot exist without a link to an existing student. This concludes our review of the 6 transformation rules. We have traveled the full path of the algorithm, from a conceptual diagram, entities and relationships, to a concrete set of interconnected tables, relations. As we have seen, the 2 key tools that made this transformation possible are the primary key, which uniquely identifies each row, and the foreign key, which physically implements the link between tables. But here a logical question arises. Is it enough for us to simply create these columns in the tables for the entire system to work correctly? Of course not. If we simply create a group ID column in the students table, what prevents us from entering a group ID there that does not exist in the groups table? This will lead to the appearance of orphan records and data corruption. Therefore, these keys are not just data but enforcement mechanisms. For the model to truly guarantee the validity of our data, we must define strict rules that govern the behavior of these keys. This brings us to the next fundamental topic, integrity constraints. With this, we begin the third section of our lecture. In the previous section, we established that primary and foreign keys are fundamental tools for building our logical links between tables. However, as I already mentioned, simply defining these attributes in the schema is not enough to guarantee correctness. We must answer the question: what mechanisms guarantee that these links will not be broken during the daily operation of the database? Imagine a situation. Without additional rules, nothing prevents an operator or program from registering a new student and entering the value 99 in their group ID column, while no group with such an ID exists in the groups table. This creates an orphan record and leads to the destruction of data logic. To prevent such anomalies, the relational model introduces a key concept, the integrity aspect. This is not just a recommendation, it is a set of strict rules known as integrity constraints. It is these constraints that turn our tables from a simple data repository into a secure, structured, and internally consistent system. Let's look at the three fundamental types of these constraints. So, we consider the first and most important guarantee. It is called entity integrity and is entirely focused on the primary key. The rule sounds absolutely categorical. No attribute that is part of the primary key can ever have a null value. Why is this so important? Let's recall that null in databases does not mean zero or an empty string. Null means value unknown, or missing. Now imagine if we allowed student ID, our primary key, to be null. This would destroy the very idea of identification. How can we enroll a student in a course if we don't know exactly which student we are enrolling? Moreover, this violates the very mathematical principle of the set we talked about at the beginning. If student ID could be null, theoretically we could have several rows with null in this field in the table, and the system would not be able to distinguish them. This would create duplicates, which is forbidden in the relational model. Therefore, the primary key must always have a specific, unique value. This is the first guarantee of the model. The second fundamental guarantee of the model is called referential integrity, and it is entirely focused on the behavior of the foreign key. If the first guarantee, entity integrity, protected row uniqueness, this guarantee protects the correctness of links between tables. The rule here is also very strict. It states that the value we try to write into the foreign key column, for example, group ID in the students table, must meet one of two conditions. First, and main, this value must already exist as a primary key in the table we refer to. That is, we can add a student with group ID equals 5 only if a group with ID equals 5 already exists in the groups table. The second condition is null. We can leave group ID empty, null, if our business logic allows it. For example, a student submitted documents to the university, but has not yet been enrolled in a specific group. This is a valid state. Most importantly, this constraint protects us from orphan records. The system will physically not allow us to create a student with a group ID 99 if group 99 does not exist. Any attempt to do so will result in an error. Thus, the model guarantees that we will never have data pointing nowhere. And finally, the third, last, but most fundamental guarantee of the model is domain integrity. Remember, at the very beginning of the lecture, when we introduced terminology, we defined the concept of domain. We said it is a set of permissible values for a column. It is this constraint that guarantees that these rules are followed. In practice, this is implemented firstly through data types. If we define the data column as date, the system simply won't let you write the text string hello there. This is the lowest level of protection. Secondly, these are more complex rules. The best university example is our grade. Its data type is integer. But that is not enough. A number can be -50 or 200. Therefore, we add a domain constraint. Integers in the range from 0 to 100. This constraint guarantees the semantic correctness of our data at the most basic level. So, we have finished reviewing the third section of the lecture. Let's quickly summarize. We looked at three fundamental guarantees, or constraints, provided by the relational model. Entity integrity, thanks to the primary key, guarantees that every row in the table is unique. Referential integrity, thanks to the foreign key, guarantees that we cannot refer to non-existent data, protecting us from orphan records, and domain integrity guarantees that only correct, admissible values are stored in our columns. Together, these three rules create what can be called a secure and internally consistent storage environment. We can be sure that the data in our database is correct and reliable. However, as noted in the summary, the model would be incomplete if it only described these static storage rules. Having ensured data integrity at rest, our next logical step is to consider the processing aspect. That is, what mechanisms and operations exist to effectively manipulate this protected data. We have finished reviewing the static part of the model, how data is structured and protected. Now we move to the dynamic part, how we manipulate this data. The revolution brought about by COD was not just in organizing data into tables. It fundamentally changed the approach to interacting with data. To understand the importance of this, let's look at how it worked before. Previous hierarchical and network models required a so-called procedural approach from the programmer. This means that the programmer had to write a detailed step-by-step algorithm, a real route to the data. The summary gives a great example. The programmer literally wrote instructions. Take the pointer to the university record, find within it the list of pointers to faculties, go to the first pointer, check the faculty name, if not the one, return and take the next pointer, and so on. As you understand, this was incredibly complex and, worst of all, fragile. The program logic was rigidly tied to physical data storage. If the database administrator decided to change the file storage method, optimize the structure, all program code relying on old pointers instantly stopped working. The relational model offered a radically different, much more powerful solution. On the previous slide, we saw the fragility and complexity of the procedural approach of old models. The relational model proposed a solution that is today the absolute industry standard. This is the concept of data independence. It means a clear separation of the logical level, that is, how the programmer or user sees the data, from the physical level, that is, how this data is actually stored on the disk. Thanks to this, a fundamental shift in approach occurred. The user no longer needs to describe how to get to the data by prescribing navigation via pointers. Instead, they only declare, that is, describe what they want to get. And the language for this declaration became SQL, the structured query language, the study of which is a significant part of our course. For example, instead of the complex navigation procedure we discussed, the user now simply writes, select names from students where group ID equals 5. This is a declaration of the desired result. And the database management system itself bears full responsibility for how to find these students, which indexes to use for this, and how to most effectively optimize this query. The program logic remains clean and independent of the physical data structure. On the last slide, we established that SQL is our declarative language. But this language did not emerge from nothing. As noted in the summary, although we do not study formal relational algebra, we must understand that SQL is based on a set of clear conceptual operations. The main property of these operations: they always take one or more tables as input data, and always return a new table as a result. We will consider three main operations that are the foundation for SQL. First, selection filtering. This is the ability to select rows. We tell the system, take the students table, but give me only those rows where the value in the group column equals 5. This is the logical basis for the future where operator, which we will study. Second, projection. This is the ability to select columns. We say, take the students table, but I am not interested in all information, give me only the surname and name columns. This is the logical basis for the list of fields in the select command. And the third, most important for understanding the model, is join. This is exactly the mechanism that allows us to assemble back that complete picture of data that we deliberately divided into many tables while performing transformation rules. This is an operation that combines tables by their keys. This concludes the overview of the processing aspect. We have a complete picture, we know how to structure data, how to protect it, and how to manipulate it. Now it's time to analyze all the advantages and disadvantages of this approach. We have finished reviewing all key aspects of the relational model. We know its structure, its guarantees, and its operations. Now we have a complete picture. and can conduct an objective analysis of its advantages and disadvantages. Let's start with the advantages, most of which directly flow from what we have already discussed. First, simplicity and unity. Unlike the chaos of network or hierarchical models, the relational one offers a single, intuitively understandable construct, the relation, i.e., a table. Everything in the database is a table. Second, data independence. This is perhaps its most revolutionary advantage. Thanks to the declarative approach we just reviewed, the programmer no longer needs to know how data is physically stored. They write a logical query SQL, and the DBMS decides how to execute it. This allows optimizing data storage without breaking the code of thousands of applications. Third, guaranteed integrity. As we analyzed in detail in Topic 3, the model is not just a repository, it is a guardian. It has built-in mechanisms, primary keys, foreign keys, and domains, that ensure data validity at the base level itself. And fourth, declarative access via SQL. Instead of complex procedural navigation code, we have a powerful standardized language. But, of course, such a design has a flip side. For these advantages, a certain price has to be paid, which we will consider on the next slide. On the last slide, we considered the obvious advantages of the relational model. But, as I mentioned, a price has to be paid for these benefits. The disadvantages of the model are a direct consequence of its advantages, in particular, the strict transformation rules we learned. First, and this is the main trade-off of the model, the join performance problem. Recall the second section of the lecture. Rules force us to take integral objects like an order in an online store and split them into many separate tables, orders, customers, order_items, products. To assemble them back into a single report, we are forced to use the join operation, which we defined in the penultimate section. These join operations are the most computationally heavy and resource-intensive for any DBMS. Second, the complexity of the logical structure. This is the same disadvantage but from a human point of view. When, as a result of following all rules, 500 tables appear in your project, simply understanding the schema and how data is related becomes a major challenge. And third, the limitation of modeling itself. The strict, flat, two-dimensional structure of a table is perfect for financial or university data, but it is ill-suited for all data types. For example, it terribly models social network connections, who is a friend to whom, or family trees. For such tasks, other, non-relational approaches are much more often used today, for example, graph or document-oriented NoSQL databases. We reviewed the advantages and disadvantages. The last, final step of our lecture remains. And so we have reached the finale of our lecture. We analyzed the advantages and disadvantages of the relational model. Now let's return to the problem with which we, in fact, started. Remember, in Lecture 1, I showed an example of a flat table, where data about students and their curators were stored together? We proved that such a data structure is inefficient because it generated three types of critical anomalies: update, deletion, and insertion. Throughout today's lecture, we found out that the relational model solves this problem fundamentally. Its transformation rules simply force us to split this data into two separate entities, students and groups. But here a key engineering question arises. How do we prove that our new design of two tables is now good or optimal? How to ensure that we separated the data correctly or sufficiently? Where is the guarantee that our new design, which in a real project can consist of 500 tables, does not hide some other more complex anomalies or data redundancy? Here we cannot rely on intuition. We need a formal process similar to a quality test that we can apply to our schema. This formal process of verifying and improving the logical model design is called normalization, and our next lecture will be dedicated to it. This slide lists three key questions from those we considered today. They relate to the most fundamental aspects of the lecture. Implementing 1. M relationships, resolving M relationships, and understanding the difference between declarative and procedural approaches. Try to answer them yourself after the lecture to check how well you have mastered the material. The full list of 10 control questions covering the entire lecture is at the end of your lecture notes. Please be sure to familiarize yourself with it. Thank you all for your attention. If you have any remaining questions regarding today's material, my contact details, email, are on the screen. please do not hesitate to write. That is all for today. Have a good day.